Welcome to the Plant Breeding and Genomics Community of Practice webinar, How to Use Doubled Haploids to Improve Winter Wheat. My name is Heather Merck, and I'm the Content Coordinator for PBG and your host today. For those of you unfamiliar with the Plant Breeding and Genomics Community of Practice, also known as PBG, I invite you to explore our training resources at www.extension.org/plant_breeding_genomics. I also invite you to subscribe to our newsletter, PBG News, and I put a link to that up in the chat pod. And that'll help you stay up to date with PBG webinars and news about other online content. During today's webinar, Drs. Bill Berzonsky and Melanie Cafe-Tremmel of South Dakota State University welcome us to their winter wheat breeding program. Dr. Bill Berzonsky is Associate Professor and leader of the South Dakota State University Winter Wheat Breeding Program. He assumed this position in September of 2008. He received a PhD in agronomy from the University of Missouri in 1988, an MS in plant sciences from the University of Delaware in 1984, and a BS in botany from the University of Maryland in 1982. As a participant in the WCSIA project, he is charged with implementing breeding techniques and strategies to promote the development of winter wheat varieties for the prairie pothole region of South Dakota and the surrounding areas. Dr. Berzonsky will begin today's webinar by discussing theory and application strategies of double haploids in wheat breeding, and Dr. Cafe-Tremmel will then provide us with in-depth discussion of the details of the double haploid technique. I'll now turn things over to you, Bill.
Okay, as Heather mentioned, what we're trying to do today is give you an overview of the doubled haploid project and particularly how we apply it in the winter wheat breeding program. And today, as Heather mentioned also, I will talk about strategy and how we try to apply doubled haploid technology in the winter wheat breeding program. And the division of labor is Dr. Cafe-Tremmel will basically talk about the details or the nuts and bolts of the doubled haploid technique. So we'll begin with a brief discussion again of strategy and how we try to apply this in our breeding program. I think to start with, we really need a definition of what a doubled haploid is. And basically the one that I come up with is a very simple definition that we're moving plants rapidly through to homozygosity, or the two-end stage from the haploid organism stage without traditional self-pollination. So this is a key factor involved with producing doubled haploids, in that we produce them very rapidly compared to the traditional technique. The other thing I should mention before we go on is that we're really talking about its implementation in a winter wheat breeding program. And there are other crops, of course, that the doubled haploid technique is applied to, but there'll be some subtle differences and important differences that we can try to point out, but we won't have that much time today to talk about anything else than mainly the application to winter wheat breeding program. So when we look at the difference between a traditional and doubled haploid method, this slide kind of illustrates some of the differences that we are talking about here. On the left side of this slide, as you look at it, is the traditional type of breeding scheme where we would cross our parents, derive an F1 from that particular cross, and then go through a series of selfing. Since wheat is a self-pollinated crop, we'd go through a series of self-pollinated generations. I'm illustrating about 5 different self-pollinated generations here, where we would get fairly close to homozygosity at the final stage of that particular breeding process. On the right side, though, you can see the difference. If we apply the doubled haploid technology directly to those F1s, probably in one generation, more likely 2 generations in terms of increasing seed and so forth, we would be at homozygosity. Furthermore, even though I don't illustrate it on this slide, we'd be at 100% theoretically homozygosity for the doubled haploids, as opposed to the inbred line at this stage. That would be kind of, well, I don't know, be fairly close to homozygosity, complete homozygosity, but of course we never completely get there through the selfing, traditional selfing process. So this illustrates it a little bit more closely, what we're talking about here. Again, on the left side, traditional pure line breeding scheme as we go through this scheme, and you can see some of the major advantages to the doubled haploid method. One of the major advantages is really in a time savings for this particular technique. On the left side, again, you see the traditional, and as I said in the previous slide, you really don't get to 100% homozygosity even after the 7th generation or 7th filial generation. Okay, whereas almost immediately after producing the doubled haploids, of course, you're at 100%, and then there'll be a couple of generations of seed multiplication, selection, and yield evaluations. So in reality, we're probably cutting off, in our estimation, as shown here in this slide, 2 years from the method as compared to the traditional, something along those lines. Now that doesn't sound like an awful lot, but it certainly is, particularly if you continue to apply this technique throughout your breeding program. Okay, so again, some of the major differences is a time savings in the doubled haploid, and we're going to talk in a few more minutes about another major advantage to the doubled haploid is because you're reaching homozygosity so quickly that you can select on complete homozygosity, which is a more efficient way to practice selection in your breeding program. So again, this technique, as I said, is not only applied in wheat, but quite extensively anymore. If you read the literature, it's applied also to corn. And you can see here just a representation of how it might be applied in deriving inbred lines in corn hybrid development. And one of the advantages with corn is, as I said, we won't have much time. We really won't have time to get into that. We're talking about wheat, but in the case of corn, to derive these inbred lines much earlier than the traditional way also gets you to a stage where you could start to test for combining ability and use tester lines to test for specific and general combining ability in a corn breeding program much earlier than in a traditional sense. Okay, so when we think about the strategy and the actual application of this technique to plant breeding, one of the things you should think about as a breeder or somebody thinking about the strategy is that what we're really doing, of course, is sampling adequate genetic variation from the initial cross. And so what I want to stress is that we do not want to somehow bottleneck or limit that genetic variation as we go through this particular process. And that's pretty much the case no matter what kind of breeding technique we're talking about, but it becomes very important in the development of doubled haploid lines because it's directly tied to the number of doubled haploid lines and the efficiency and effectiveness of actually producing the doubled haploid lines. So this is why Dr. Cafe-Tremel will talk a little bit later about the importance of trying to improve the technique and trying to produce as many doubled haploid lines as you possibly can do in your breeding program from the initial cross. Because again, we're really basically sampling the genetic variation from that initial cross. There's other ways to apply the technique that we might get into a little bit later. Could actually be applied instead of at the F1 stage, maybe at the F2 or F3. There's some advantages to that, but there's also some disadvantages that maybe we'll get a chance to talk about a little later. Okay, as we talk about the advantages and disadvantages of the doubled haploid technique, I really think it's kind of nice to think about the breeding program as not much more than a factory type situation. And that's why I've got this graphic up here now to kind of illustrate the advantages in this analogous situation to what we're trying to do with the doubled haploid technology. So if you think about the breeding program as a whole, as a factory, when we look at the crossing of desirable parents at the beginning, what we're doing here, of course, are entering our raw materials into this factory. Okay, and as we go through the processes that are done in this factory, what we're talking about in the traditional breeding sense is all the evaluations, the yield trials, the testing for quality, the testing for other kinds of traits, and the selections we're making on those particular lines and plants to derive the types of traits that we want. In the end, of course, the final product to come out of that factory, somewhere like 10 to 12 years down the road, as we tried to illustrate earlier, is the release of the variety. So the variety is the final product. So I think keep that vision or analogous picture in your mind as we try to talk about some of the advantages and disadvantages of the technique. So some of the advantages to using a doubled haploid type of procedure in this particular, again, thinking about the breeding program as a factory, first of all, is that homozygosity is achieved very rapidly, as we mentioned before, and essentially one step or a couple of steps if you include some of the seed increase that needs to be done. Okay, so we're actually improving or increasing the throughput of that particular factory in doing it this way. The next thing is that we can practice in the internal part of the factory. We can now practice what I like to call safe selection, because now we're selecting on true breeding plants. And what I mean by true breeding is that the plants that are completely homozygous are going to perform very much, the progeny from those are going to perform very much similar to the generation that we're making selections in. So not only are we improving the throughput of the factory, but we are improving the quality of what we do in the factory by improving the selection. Furthermore, selection is now based mainly on additive gene effects, of course, once you get to homozygosity. And most breeders and geneticists, of course, will realize that if you're selecting on additive gene action, you really are making permanent genetic gain and very nicely achieving permanent genetic gain. And so this is something we also want to do, and that's what doubled haploid technology allows us to do as well. And of course, in the case of wheat, homozygous source of seed is really important in the end, because this is what we're releasing as the variety through what comes out of the end of the factory process here. And finally, as I said, in the case of something like a cross-pollinator like corn, it's a rapid way to produce inbred lines for more efficient testing or earlier testing of combining ability in terms of how those inbred lines will perform in the final hybrid. So as we consider what it does to our breeding program, thinking again about it as a factory, basically the quality control and the efficiency of our factory is improved. That's the internal workings of the factory, what we're doing in there during selection, and progressing lines through selection is improved. Okay, the time to product output, or the throughput of the factory itself, is very much improved by the use of doubled haploid technology. And then something I'm going to talk about in a few minutes that's probably, in my mind, one of the most important things that's being improved in terms of what we do from a breeding standpoint is the sustainability of this factory production. So if we continue to improve our output in time and our quality control over several cycles of breeding, it's going to improve in the long term the sustainability of our factory production. So when I talk about this kind of sustainability, I like to talk to it thinking about what breeders typically talk about as parent building. Okay, and in fact, when I think about plant breeding in general, I think about it as a parent building endeavor. So we're always building on what we've done in previous cycles of plant breeding. Even our predecessors, Heather mentioned that I came here in 2008 to South Dakota State, and I just continue to build on, as most breeders do when they come into a program, on the work of my predecessor. Okay, and the reason this parent building works so well is because a breeding process is really a cyclical process, as you can see on this particular slide here. Okay, we start with crossing desirable parents, as we mentioned in a previous slide. We evaluate the offspring from that cross. We select the highest performers, and then hopefully, of course, one or two of those lines will be released as varieties. But if they are not released as varieties, we just typically don't throw them out because we've done a lot of work up to this point. So they're recycled back into the breeding program as advanced lines and new parents to be crossed again. So anytime you can improve and make this more efficient, this cyclical process, and the throughput of this in the long term, you're going to improve the parent building process. Okay, I happen to find this, and this is from a particular presentation that was given by Barkley and Chumley, I believe, who are actually, Forrest Chumley is actually the CEO of Heartland Plant Innovations, who are producing doubled haploids in Kansas on a commercial scale. And as they were proposing to build their facility there in Kansas, they were trying to document the benefits to using a doubled haploid type of technique in their breeding program. And so what they're showing here is that they projected that if they had started their doubled haploid program and their facilities were built in 2011, okay, 7 years down the road, they're going to start to realize the benefits of the doubled haploid procedure. And their projections are, believe it or not, that because of the efficiencies in selection and so forth, the advantage is going to be like 150% increase in terms of the yield of doing a traditional baseline breeding approach. Okay, again, keep in mind this is theoretical and not actual, but at least that's one of the things that they projected. So we've talked about some of the advantages to this particular approach. Let's talk about some of the disadvantages, because as almost any breeder will realize that you incorporate something in your breeding program, it seems to improve the efficiency or effectiveness, but there always seems to be some drawback that you have to also be mindful of in doing this type of procedure. In the case of doubled haploids, remember when we think about the traditional technique that we are selecting as we go to homozygosity all along the way. Okay, we've sort of done an end around or bypassed that type of situation when we do the doubled haploid technique, and in doing so, we reach homozygosity so quickly that we haven't had a chance to really look at those lines very extensively or hardly at all, and so there is a lot of poorly performing lines at that particular stage. So we really need to be mindful of that. And taking this shortcut, that's one of the problems that arises. Okay, we talked about whether this technique could be applied either at the F1 stage or later in the breeding program. One of the advantages to waiting a little bit later and applying it maybe to an F2 population or F3 would be that we would take advantage of more recombination between those initial traits incorporated from the parents. Okay, if we do it on the F1 as is traditionally done, though, not very much recombination is taking place, particularly compared to the traditional type of inbreeding process before things are fixed at the homozygous stage. Finally, success is sometimes unpredictable and can consume valuable resources. I think this will come out quite substantially as Dr. Cafe-Tremel talks about the resources and so forth and some of the difficulties related to actually doing the doubled haploid procedure. So I won't get into that very much, but it is definitely a disadvantage. Okay, so I just wanted to illustrate one example. This one's in the literature. It's fairly old now, from 1990, but I think it's a nice illustration of an example. This one was actually proposed in the way to apply doubled haploid technique to barley in terms of taking an adapted parent. In this case, we would call parent 1 the adapted parent. Parent 2, we're trying to move in a gene or genes maybe from an exotic source into parent 1, maybe for disease resistance or something like that. Okay, so their idea of applying the doubled haploid technique is to produce the F1 from this cross and then apply a doubled haploid technique or the doubled haploid process to the F1s. And once all these lines are fixed at the homozygous stage, they take advantage of the power of selection at that particular point because now all these lines are true breeding, and they would perhaps select these lines in a greenhouse, for example, for disease resistance, take the selected lines in the following generation and backcross that to our adaptive parent, parent 1. Actually, the procedure that they outlined was more or less a cyclical type of process and alternating the doubled haploid step with this backcrossing process, more like a recurrent selection type of thing here, as the title of the paper illustrates. But I think it illustrates the very nice process and way to apply the doubled haploid technique in a breeding program. Okay, before we get to Dr. Cafe-Tremel, I just want to summarize what I've been talking about, reiterate that we are actually doing this in our breeding program here as part of what Heather mentioned as Winter Cereal Sustainability in Action, or what we tend to call WCSIA. This is a program that's been sponsored and funded by Bayer Crop Science and working with Ducks Unlimited. Okay, the idea is that, of course, Ducks Unlimited has shown that in the prairie pothole region of South Dakota and North Dakota, which is kind of this blue area here, that that duck nesting is favored when the nesting habitat is not disturbed in the spring of the year. And of course, in winter wheat, we're planting into no-till in the fall, and there's no disturbance as opposed to spring wheat in that habitat. So this is the idea of promoting the production of winter wheat from a Ducks Unlimited standpoint. Okay, I need to emphasize that we're not producing doubled haploids for a service or on a commercial basis. But if you are interested in doing that, at last check from Heartland Plant Innovations, they were charging $30 per haploid line to produce doubled haploids. In our case, we're applying it specifically to focus on developing winter hardy and disease-resistant winter wheat varieties for this prairie pothole region, as Heather mentioned. I just wanted to, before I get to a summary of what I talked about, also kind of illustrate how extensively this technique has been applied from our colleagues to the north of us in Canada, which shows that they've been working with doubled haploidy a little bit longer and implementing the technique in their breeding programs. But you can see I've put this chart together, or this table together, from the table from this publication from Ron DePauw and several others. from the Canadian breeding programs, and you can see that in all of the Western Canadian wheat classes, there has been at least one, in some cases more than one, variety released using the doubled haploid technique, or at least applying the double haploid technique in the development of these varieties. I counted these up the other day. Turns out to be about 25 different varieties have been released through the Canadian breeding programs with the use of doubled haploid breeding. And all these different institutions at one point or another have also been involved in developing varieties using the doubled haploid technique. So it does work, and does work successfully as you incorporate it into your breeding programs. Other thing to mention is in terms of winter wheat, in the winter wheat classes, it's probably even a more important and valuable technique than sometimes for the spring wheat, because we also have the vernalization requirements as opposed to spring wheat, and so we can't take advantage, as they do in spring wheat so much, of off-season nursery. So any other way we can speed up the breeding program is very nice in the case of doubled haploid technology. So I'm going to summarize these and then hand this part over to what I've been talking about, and then hand it over to Dr. Cafe-Tremble to talk to you about the nuts and bolts of the procedure. But to summarize, applying doubled haploids to breeding must be implemented, in my mind, to achieve a single focused objective, unless you are trying to use it or trying to apply it in a commercial sense, because of how much resources and other things are involved. It really needs to have more of a focused approach, I think. Key is to get doubled haploid production efficient enough and at a high enough level to adequately sample the F1 genetic variation, as we talked about before. Must have dedicated full-time personnel and adequate facilities for the doubled haploid production. I think this will shine through in what Dr. Cafe-Tremble talks about as well, but we've really found this to be the case. Every time I've been involved in doubled haploid production, it's very important, I think, to really do it successfully, to have a dedicated individual and facilities to this. As a breeding tool, its biggest benefits are mostly long-term in my mind, in the parent building, improving the effectiveness of selection, and of course hastening the variety release over years. The take-home message I just wanted to leave you with, again on the strategy or applying the double haploid techniques, is that the benefits to applying the technique in wheat are primarily, at least in the short term, improving the power of selection. We talked about quality control and efficiency, and in the long term, building and improving parents. And again, that relates to the time and sustainability in terms of that factory analogy that we